Hey everyone, this is Matt, and it's part 2 for this problem, and we're solving for the adiabatic flame temperature of methane as it burns with an excess amount of air. So to solve for this temperature, we want a function of temperature, of course, and to do this, we're first going to start out with a normal mass-energy balance equation. We know that the changes of the mass's internal energy, its potential energy, and kinetic energy going to be equal to any heat added to the system plus any non-work flow plus changes in the enthalpy, potential energy, and kinetic energy going in minus the changes in enthalpy, potential energy, and kinetic energy going out. And so it's an adiabatic system, so heat is going to be equal to 0. And we're going to assume no non-flow work here, so there's no stir or mixer going within the system. So non-work flow is equal to 0. And there's no changes in the actual material inside the system, and it's a steady state system. And so this term is also equal to 0. So now we know that the changes of enthalpy, potential energy, and kinetic energy going into the system is equal to the changes in the enthalpy, potential energy, and kinetic energy going out of the system. And so to solve for a function of temperature to allow us to find the adiabatic flame temperature of the system, we can use enthalpy here. And so we know that the changes in enthalpy going in is equal to the changes in enthalpy going out. And so how can we solve for just a function of enthalpy rather than a function of changes in enthalpy? Well, first of all, it's worthy to note that the enthalpy of our system with all components I is going to be a summation of all components I. So the components are going to be carbon dioxide, methane, water, and so it's going to be summation of all components I of their moles of each component times their respective enthalpies at whatever temperature they're at. And so we want to find a solution or an equation here for enthalpy as a function of temperature. So enthalpy relies on a couple things, and so we can say the enthalpy of a species is going to be equal to the standard enthalpy of formation of an ideal gas, and that's actually just given to us, and plus, what is it going to vary with? So it's going to vary with temperature, which is what we want. And so we can say that it will vary with the changes in the specific heat capacity of the component, and that will vary with pressure or temperature. And we want to vary it with temperature, so we can hold the specific heat capacity at constant pressure and allow temperature to vary. So we can say, we can put plus specific heat capacity held at constant pressure with respect to temperature. And we want to vary it from our normal temperature of the atmosphere, 298.15 Kelvin, and to any temperature here. So now we can solve for the enthalpy of a component using the enthalpy of formation of an ideal gas plus the integral of the specific heat capacity at constant pressure with respect to temperature from 298.15 Kelvin to whatever temperature we want it to be. And we can use this equation here after we evaluate this term to solve for the temperature of the flame as the methane burns in an excess amount of air.